Hello everyone. So yesterday we discussed maximal margin classifier. So maximal margin classifier was applicable only when you have linearly separable classes. So of course the first question arises, what if my classes are not linearly separable? Okay. And there is another issue. It's not just about separation, but we also saw that my classifier perfectly categorizes the training data. So the maximal margin classifier, so if you have, for example, say bivariate data set, and suppose this is one class, and suppose we have this as another class, then we are getting, so if suppose these are two classes, then my maximum margin classifier goes kind of from in between these 2 points, right, the closest points. So it is something like this, so that this and this is margin. Okay, let us assume they are equal. Now suppose there are some changes in certain vectors, and especially the support vectors. For example, if I get some blue point over here, then what would happen? Then my classifier is going to change. So I might get a point going from in between these 2 points. So something like this as my new classifier. So even if one point is added, my classifier equation has changed quite drastically. Okay, originally it was the black line, now it is the green line. So the equation has changed quite drastically, and in addition to that, the distance of the support vectors from the classifier has also decreased, which means that the margin is very low now. And we have already seen that the margin indicates kind of confidence. So higher the margin, more confident you are about your allocation. So this means that this second classifier, even though it still perfectly classifies everything, is not as we won't be as confident about our prediction as in the case of earlier classifier. So what happens is, this is our classic problem. Because my current classifier, maximal margin classifier, is perfectly working on the training data, it might actually be overfitting the training data. As soon as I try to predict a new observation, I might get very incorrect results. Okay, because this classifier is tuned in such a way that it is perfectly classifying the training data. So the question of overfitting would always remain. Hence, to address both these points, first the non-separability and second this overfitting, we need to do some modification. So that modification we are going to do via support vector classifiers. Okay. So how does maximal margin classifier change from to get a support vector classifier? So whatever is problematic, we try to eliminate that. So first thing is, what if we don't have perfectly separable cases, right? So maybe our classifier should allow for few misclassifications. Okay, at least for few misclassifications, it should have a way to address them. So that even if my classes are not perfectly separable, I can still work with this. Okay. And the second problem is overfitting, that is automatically taken care of if we allow few misclassification. In fact, here we would say few misclassifications might be better than no misclassification at all, even in a perfectly separable case, because in that case my classifier may be more amenable for prediction. So it may not be overfitting, so it may be okay. So on training data it gives decent results, and on test data also it will give me decent results. Okay. So allowing misclassifications means what? Now there are 2-3 components to it. So my original classifier supposes this, and this is my kind of margin. So what we know is certain observations are here and the other class of observations are here. So whoever is on the margin acts like a support vector. Okay. Now what is meant by allowing misclassification? There are 2-3 things. First of all, I can allow violation of margin, okay, What do I mean by violation of margin? So I can allow some observations of this class to be here. So they are on the wrong side of the margin, but they are still in the correct class. Getting it? So I am still on the same side of the hyperplane. So this is my original hyperplane, and dotted lines are margins. So these points are on the wrong side of the margin but still in the correct class. Similarly, I can have a few points here. So these are again on the wrong side of the margin but on the in the correct class. Okay. So this is one possibility. And another possibility is allowing actual misclassification. Means allowing some points to go somewhere here or here, and points from this class to come somewhere here or here. Okay. So these two types of violations are possible. So if we decide that okay, we are going to allow both these types of violations, then probably we can reduce the overfit. Okay. And of course we can also handle non-separable cases, because yes, some of the observations are allowed to be on the wrong side. So if they are not clearly separable, it's fine. We will try to work with the scenario which is in some sense optimal. Okay, just like regression line. We cannot have everything exactly on the line, but we try to find a line which is optimal in some sense. Okay. So how would we do that? So we will have to modify our optimization problem, because currently our optimization problem ensures that there are no such things allowed. So we will modify our optimization problem and try to accommodate these things. Now how to modify? Let us write down the problem new statement first, and then we will try to discuss how the new terms work. Okay. So the basic principle still remains the same. We try to maximize the distance between the two classes, and we call this distance as margin. So we try to maximize, this is margin, so total is 2m. So we try to maximize m. We try to choose beta naught, beta 1, beta 2, beta p. In addition to this, we are going to introduce new variables epsilon 1, epsilon 2, epsilon n. So basically one variable for each observation from the training set. So maximize m subject to summation beta j square equal to 1. J goes from 1 to p. So this condition remains as it is. No change there. In the next statement, we are going to introduce epsilons and make a small change. So the next part initially said yi into beta naught plus beta 1 xi1 plus beta 2 xi2 plus beta p xip should be greater than or equal to m. This was my initial statement, right? So basically, if equation of the hyperplane, when you substitute xi's in it, if it gives you negative value, then you allot it to class -1 so that the product is positive, and you make sure that it is greater than m so that the margins are preserved or retained. Now here, instead of just m, we are going to bring in 1 minus epsilon I. Okay. And what are the conditions on epsilons? Conditions are epsilon I should be greater than or equal to 0, and summation epsilon I should be less than or equal to c, where I goes from 1 to n. Note, c is not a parameter. Right now I am not maximizing over c. So c will be chosen in advance, and then this problem will be solved. Of course, we can try with different c's. We'll discuss it later. Okay. First of all, what is this? What is the role of epsilons here? Now see, we are saying epsilons are non-negative. What happens if every epsilon is 0? If every epsilon is 0, I actually get back my original problem, that is maximal margin classifier. Okay. Now, if we allow some epsilons to be positive, what does it mean? Let us say epsilon 1 is positive, and we will assume that it is less than 1. So 1 minus epsilon is a number between 0 and 1. Correct. So what does it mean? Let us just for the sake of convenience, let me assume epsilon 1 is 0.5. So I get this right hand side to be m by 2. So what do I mean by this? For the first point, my constraint now becomes y1 into beta naught 1 plus beta 1 x11 plus beta 2 x12 etc. should be greater than or equal to m instead of greater than or equal to m by 2 instead of m. It means that I am allowing violation of margin. So let us go to the picture that we were drawing here. Okay, so this total distance of one class from the boundary is m. So m by 2 would be somewhere here, right? So we are saying that it need not be greater than m, it can just be greater than m by 2. So I am allowing a point to be here instead of completely here. Okay, on either side. Okay, even in this class I am allowing the same thing. I am allowing points to be here rather than completely here. Okay, so this is violation of margin. Okay, I took 0.5 as an example, but basically depending on epsilon you will allow everywhere between the hyperplane and the margin. Okay, so epsilon being positive and less than 1 allows for violation of margin. And what happens if epsilon is greater than 1? So if a certain epsilon I is greater than 1, then this quantity would become negative. If this is negative, it means that we are allowing this product yi into hyperplane thing to be negative. We are allowing it to be negative means we are allowing misclassifications. Okay, so for those epsilons for which epsilon is between 0 and 1, we are allowing violation of margin, and for those epsilons which are greater than 1, we are allowing not only violation of margin but we are also allowing misclassification. We are allowing that observation to go in on the exact opposite direction. Okay, so this is how we bring in certain violations, and hence this classifier is known as soft margin classifier. Okay, why soft margin classifier? Because initially our margins were hard, we were not allowed to violate those margins. Now we are allowed to violate the margins, so they are called as soft margin classifiers. You can kind of bend through them. Okay, these epsilons are actually called as slack variables. Okay, you say cut some slack, so you are actually cutting some slack for few points. So these epsilons are called as slack variables. Okay, what is this C? C is actually known as tuning parameter. We are saying summation of epsilons should be less than C. If C is 0, of course every epsilon has to be 0. So C0 forces us to go back to maximal margin classifier. Okay, if C is positive, then we can have something different, which is support vector classifier. So this statement is actually for support vector classifier, this entire problem statement. Okay, so if C is positive and epsilons are, if suppose epsilons are greater than 1, then it would mean greater than or equal to 1, then it would mean summation epsilon I going from 1 to n should be less than C, implies at most C epsilon i's can be greater than 1. In fact, not even that. Okay, at most C epsilon i's can be greater than 1, because then only the summation would be less than C. What does it mean? It means that at most C observations can be misclassified out of n observations. Okay, let me repeat. At most C observations would be allowed to get misclassified from out of all n observations. So what happens is, this C kind of becomes an upper bound about how many violations are allowed or up to what severity they are allowed. So if epsilons are between 0 and 1, Still, if we want sum to be less than C, then up to what extent margins can be violated? So C controls the count and severity of violation. Count and severity of violations is controlled by C, and C is known as tuning parameter. So we can experiment with different values of C, and by cross validation we can choose the best C, because after all our final aim is prediction. So best C can be chosen via cross validation. Now what are support vectors in this context? So here, of course, points which are on the margin are support vectors, and points which are on the wrong side of the margin are also support vectors. Okay, so the number of support vectors here might increase because you are allowing points on the wrong side of the margin, so they all become support vectors. Now what is the effect of C on support vectors? If C is very small, then very few violations are allowed, and if very few violations are allowed, then to accommodate the same data set with less violations, you will have to make your margins very narrow so that everyone is following the margin. Getting my point? Perhaps not. Let me repeat. See, okay, let me draw picture again, separate picture. So you have some data set. So if you don't want to allow for any violations, then of course your classifier has to be something like this and your margins would be something like this. Okay, assume that the margins are touching these points. Okay, however, if you are ready to allow for some violations, then your margins can become wide. You can have something like this as a margin if you are ready to allow for certain violations. Okay, so these three would become violations, and here also those four would become violations. Okay, so as soon as you allow for some violations, your margins become large. So what do I mean by that? As C increases, margins widen. Okay, as C increases, margins widen. So if margins widen, then what is meant by that? It means that more and more observations can become support vectors, because now everyone who is lying on the margins or lying within the margins is a support vector. So more and more observations become support vectors. So if more observations are support vectors, means my final equation is based on many observations instead of few. Initially it was based on very few observations, right? Only support vectors. So when something is based on very few observations, it is not at all robust. It changes very fast, and hence its variance is high. Okay, so when your C was very low or 0, then the equation depended on less number of vectors, less number of support vectors. As a result, it was very sensitive to changes. So even if one vector is changed, the equation would change drastically. So the variance was high and bias was low, because the fit was very good. So bias was low. On the other hand, if my C is high, then I have more number of observations which become support vector. So changing one or two may not affect my final equation that much. So variance is low and bias is high, because now you are allowing too many misclassifications, so bias is high. Hence, C acts like usual tuning parameters. Choosing C is actually choosing a trade-off between bias and variance, which can be obtained via your usual cross-validation type of thing. Okay, so this is how we move on from support vector classifier, maximal margin classifier to support vector classifier. Of course, it still has some issues. This is still not perfect, Why? What if I have some strange situation? So for example, if I have classes like this, so this is one class of observations, okay, and the other class of observations if is something like this, okay, then whichever linear way I create a class, it's still not going to be that good. Okay, so separation of such types of classes cannot be done cannot be done satisfactorily via a linear boundary, right? So whatever line you draw, you're going to have many misclassifications. Okay, so to handle such scenarios, we will need to modify support vector classifiers further, and that's how finally support vector machines come into picture. Actually, many people use the word support vector machines for everything, like maximal margin classifier, support vector machine. So there is a lot of confusion over terminology, but generally, so while talking, you'll have to be careful what that person means by support vector machines. But for us, maximal margin classifier is the one where there is a clear separation, no violations of margin. Then support vector classifier is the one which is still linear, but there is no clear separation, so you might allow for violations of certain margins and even some misclassifications. And then when these two still further need to be changed, means when you need non-linear type of decision boundary, we go to support vector machines. So how support vector machines achieve that, we will see in the next lecture. Thank you.